Welcome to DRM1413 Manufacturing Technology, Chapter 5, Powder Metallurgy, prepared by Associate Professor T.S. Dr. Siti Rabiatul Aisha Binti Idris from the Faculty of Mechanical and Automotive Engineering Technology. This chapter is an engineer's practical guide to powder metallurgy, covering everything from particle mechanics to manufacturing net-shaped metallic components. We will cover 5 main topics: an introduction, powder characteristics, production of powders, the powder metallurgy process flow, and key design considerations for PM parts. Powder metallurgy offers significant economic and manufacturing gains, such as net-shape production and the use of exotic materials. However, it is capital-intensive and has size and geometric constraints. The manufacturing pipeline involves 5 main steps: powder production, blending and mixing, compaction to form a green compact, sintering for strength, and secondary operations for finishing. Metallic powders can be produced through atomization using gas or water, chemical reduction of oxides, or electrolysis, each yielding different particle shapes and purities. Powders are classified by size using screening methods, defined by mesh count. Particle morphology, dictated by the production method, influences packing and compression characteristics. The process starts with homogenization, which combines powders of the same composition, and mixing, which combines different chemistries. Various mixers are used for these steps. Compaction uses opposing punches to squeeze the powder inside a die, forming a green compact. This process increases density through particle rearrangement and plastic deformation under pressure. Sintering occurs at temperatures between 70% and 90% of the metal's melting point, and the metal remains unmelted. This solid-state heat treatment creates point bonding and develops true grain boundaries. Secondary operations address the inherent porosity of PM parts. Impregnation uses oils or polymers for self-lubricating benefits, while infiltration uses molten metal to eliminate porosity and improve strength. Mechanical operations like repressing, sizing, and coining are used to improve density, dimensional accuracy, and intricate surface details. Machining and coating are reserved for features difficult to achieve by pressing or for final aesthetics and corrosion resistance. The foundational rule of PM design stems from the physics constraint that metal powders don't flow like liquids. The ejection imperative requires parts to slide vertically out of the die, resulting in 4 classes of PM parts. Allowed features include vertical holes and vertical undercuts, as they align with the uniaxial punch action. Restricted features like side holes or side undercuts are impossible to eject without damaging the part or tooling. Proper tooling survival requires careful consideration of chamfer angles and corner radii. Acute chamfers and full outside radii are not recommended, as they can cause tooling to shatter under high-pressure compaction. The 1.5 millimeter rule defines structural minimums. Minimum wall thickness must be 1.5 millimeters to ensure even powder flow. The minimum hole diameter is also 1.5 millimeters to prevent core pins from snapping under compaction forces. Here are some exercises to review the key concepts covered in this video. These questions cover the basic steps, sintering events, advantages, mixing and blending differences, and the competitiveness of powder metallurgy.